Welcome back to linear algebra. In this video, I want to talk about orthogonal Euclidean vectors. The idea of orthogonal and perpendicular are very closely related. There is a subtle difference between two things being orthogonal to each other and being perpendicular to each other, but I will be perfectly honest, I'm not sure that I understand it myself. I have been investigating this for several years and I've never gotten a clear consensus. So when you see the word orthogonal, if you want to think perpendicular instead, that's perfectly fine. We can use them interchangeably, but in the language of linear algebra, we stick with the idea of orthogonality and we tend to ignore the word perpendicular. You might remember that for planar vectors, the angle between those vectors is defined. U dot v is equal to the magnitude of u times the magnitude of v times the cosine of theta, the angle between them. And if u is orthogonal to v, and I'll use this upside down T looking thing to mean orthogonal, that's something that will come up fairly frequently. Whenever you have two orthogonal vectors, the cosine of the angle between them is going to be 0. Right? Perpendicular lines meet at right angles. So theta could be 90 degrees, or it could be 270 degrees, or negative 90 degrees, or all of those things in radians. But the important thing is that cosine at all of those angles is always 0. And since the angle between vectors in the plane is defined using cosine, that's all we have to care about. For two-dimensional vectors, understanding the angle between the vectors is very straightforward. Looking at three-dimensional vectors, it's a little bit challenging, but you can still kind of figure it out. And trying to visualize 4 or 5 or 7 or 27-dimensional vectors is headache-inducing, and I don't want to try. But I'm going to generalize and assume that this is still true for Rn. So for any two vectors, u and v, in any dimensional Euclidean vector space Rn, we say that u is orthogonal to v, which we'll denote using the upside down T symbol, if and only if the dot product u dot v happens to be equal to 0. And two vectors is perfectly fine. That's something that's very reasonable to work with, but we're going to want to have larger collections. So let's consider a set. I'll name it S. It's going to be a collection of vectors that I will name as subscripts, v1, v2, all the way down through to v sub k, a subset of Rn. We say that S is an orthogonal set if and only if vi dot vj is equal to 0 whenever I is not equal to j. Or in other words, every pair of vectors you could select out of this set each satisfy the definition of orthogonal vectors. If you take a vector dot itself, you're going to get the magnitude of that vector, which is almost certainly non-zero, unless the vector itself is the zero vector. But that's good enough for us. The most important example is the standard basis vectors for Rn. Right? E1 is the vector 1, 0, 0, everything else 0. E2 is the vector 0, 1, 0, everything else 0, and so on down the list. These vectors are orthogonal. If you dot any pair of them with each other, the one is not going to match up with the only non-zero number in the other vector, and so you are going to always get 0. The fact that the standard basis vectors are orthogonal turns out to be one of the most important things in the geometry of linear algebra that we're going to kind of sort of mostly get to talk about in this course, but not nearly as much as I would like to. A less straightforward, but at the same time a little bit easier of an example. Consider a couple of vectors, 2, 1, negative 1, 0, 1, 1, and 1, negative 1, 1. 3 vectors as a subset of R3. To show that these vectors are orthogonal requires us to take every combination of dot product. So if we take the first dot the second, 2, 1, negative 1, dot with 0, 1, 1. Remember, dot products are pairwise multiplication. So we'll multiply 2 times 1, 1 times 1, negative 1 times 1. We'll add all of those things together. So it's 0 plus 1 plus negative 1, which comes out as 0. We'll take the first and the third. 2, 1, negative 1, dot with 1, negative 1, 1 comes out as 2 minus 1 minus 1, which is in fact 0. Right. Now on to the second vector. And we don't have to dot the second with the first because we know that the vector dot product is commutative. A dot B and B dot A always gives you the same result. The only thing we still have to test is the second dot the third. I think I have just enough space on the screen to finish this off. 0, 1, 1, dot with 1, negative 1, 1 is going to be 0, and negative 1, and positive 1, which is in fact 0. Right, so we can show pretty readily that this set is an orthogonal set. There are several things that we're going to be building on as we go through to show why orthogonal sets are valuable and useful. But the first one, the most easily accessible one, Let's start off with an orthogonal set S, same naming convention we used in the definition. And that's all we know. We have a set of Euclidean vectors, which we claim is an orthogonal set. And I claim with just that, we can go on to assume or establish that S is also a linearly independent set. Right. Linearly independent is incredibly valuable. We've talked in several lessons now. When a set is linearly independent, it can form a basis for a vector space. Not every linearly independent set will be orthogonal. In fact, most won't. But when you have an orthogonal set, then you will know it's linearly independent. And even with the one example we did, I hope that your takeaway from that is it was a lot faster to show that a set was orthogonal than it is to show that a set is linearly independent. And so whenever we have that as an option, it's really powerful and it really saves us a lot of time. The reason that this works is kind of interesting. Before I get into the proof, I want to remind you of a result that we talked about very early in the course. U dot U is equal to 0 if and only if U is the zero vector. That is going to be an important consideration in this, because I just realized that I didn't put a word in my theorem. Sorry about that. The theorem is supposed to state that S is an orthogonal set and is non-zero, because I need to know that all of those vectors are not zero. The zero vector in a set means that the set is always linearly dependent, so we do have to make that caveat. And the zero vector is also orthogonal to every vector, because you dot any vector with zero, you get zero. All right, so with that one extra consideration in mind, we can continue onward. I want to consider a linear combination, C1v1 plus C2v2 all the way down to CKvk, and choose the constants so that this linear combination is equal to 0. No matter what set of vectors you are looking at, there is always at least one way to do this. In most vectors, most sets of vectors, there are infinitely many different sets of constants where this will work. If the vectors are linearly independent, the only set of constants where this works is the zero vector. So what we want to show is that C1, C2, all the way down through to CK are all the constant 0. And the way I'm going to show that is by taking a vector v, vi, out of my orthogonal set S. It doesn't matter which one we're going to use, and in fact, throughout the proof, we have to do all of them. So I'm going to say for each vi in S. Watch what happens if I take vi and I dot it with my linear combination. Well, by a simple substitution, this is equal to vi dot with the zero vector. And anything dot with the zero vector is zero. But I could also use the distributive property. We know that the vector dot product distributes over addition. So I could instead rewrite this as C1 times Vi dot V1 plus C2 times Vi dot V2 all the way down to Ck times Vi dot Vk. And from what I said before, this has to still be equal to 0. But the set of VI's, the set of all of these vectors, is an orthogonal set. So when you dot Vi dot V1, you get 0. When you dot Vi dot V2, you get 0. When you dot Vi dot Vk, you get 0. Except for the one vector, whichever one it is, Ci times the quantity Vi dot Vi. That's the only thing that remains. Everything else has to be 0. That's what it means for a set of vectors to be orthogonal. And so we get Ci times Vi dot Vi must be equal to 0. And from there, either Ci is equal to 0 or Vi dot Vi is equal to 0. And since I said that the set of vectors are non-zero, it's not possible that Vi dot Vi is 0. That only works for the 0 vector, and I said in my assumptions that the 0 vector is not in this set. So I get that Ci is equal to 0. And I said that this is true for each Vi. So that means that C1 is equal to 0, C2 is equal to 0, all the way down to Ck is equal to 0. And all of these equal to 0 is exactly what it takes to say that these are linearly independent. The only possibility is that all the constants are 0. Which is exactly what I said I was going to prove. And as I said when I started out, the reason that this result is so important, so valuable to us, is that whenever we have a linearly independent set, it might form a basis. Not only is it easier to show that a set is linearly independent when it is orthogonal, because showing that a set is orthogonal is easier, and you can't be orthogonal and not be linearly independent. But it also turns out that whenever you have a basis which is orthogonal, there are some nice properties that come out of it that make things even nicer. The setup on this theorem is lengthy. The proof is actually fairly straightforward by comparison, and it will show us where we're going and why this is going to be so useful. Let's let W be a subspace of Rn. Let's let our set S, which is still going to be V1, V2, all the way down to Vk, and we want this to be an orthogonal basis for W. And the last thing we want is an arbitrary vector little w in vector space W. I need one other thing, which technically we have to prove, but we have proven. So remember that from the definition of a basis, there must be a unique linear combination so that C1V1 plus C2V2 all the way down to CKVK is equal to W. We know that that is the case. I'm not proving that. I'm using the fact that this is already known to be a unique linear combination. We proved that when we talked about a basis for a vector space in the first place. The claim is that each CI is equal to W dot with VI all over VI dot with VI. That's the interesting thing. I'm going to race through the proof of this. It follows the proof at the orthogonal vector set is linearly independent in the first place. It's going to be very much the same idea. If we take W dot V, W dot VI, that's the same thing as W, no, other way. W is the same thing as C1V1 plus C2V2 plus all the way down to CKVK, and we're still dotting that with VI. I can distribute and just like in the proof of linear independence, we know that the only multiplication in this that will survive is CI times VI dot VI, right? Because the set of vectors V are linearly independent, because the set of vectors V are orthogonal, every other dot product must be 0. So I get that W dot VI is equal to CI times VI dot VI, and I can divide both sides of the equation by VI. To get the result that I said I was going to get. This is an interesting result. But what it does to me and what it does to anyone who starts to really get into the rhythm of mathematics is to lead us to we could do better. because you might remember from a previous mathematics class, or even from the beginning of this course, we talked about it briefly, but we haven't done much of anything with the magnitude of a vector before. The norm or magnitude of vector vi is the square root of vi dot with vi. So I could rewrite this as ci is equal to w dot vi all over the norm of vi squared. And sure, I could write that as a theorem, but that's not really what's important. What's important is now we really start thinking, you know, this would be so much more convenient if the magnitude of vi was just 1. If we could rewrite the vector vi so that its magnitude, its norm was 1, then we'd be dividing by 1 here, and life would be so much easier. That's where unit vectors, which are also known as normalized vectors, come into play. A normalized vector is a vector q such that the norm of q is equal to 1. And you can get a normalized vector by taking any vector and dividing by its own magnitude. That's something that you've probably seen in the past. I'm not too worried about that. Now, let's look at a quick example. If I have vector v, just a two-dimensional vector, 3, 4. I chose this because it's a Pythagorean triple. The norm of v is equal to the square root of 3 squared plus 4 squared, which is the square root of 25, which is 5. And so if I divide the vector by 5, vector q is 1/5 vector v. That's in components, 3/5, 4/5. Well, 3/5 squared is 9 over 25. 4/5 squared is 16 over 25. 9 plus 16 is 25. So, excuse me, sorry about that. All right, 9 plus 16 is 25. 25 divided by 25 is 1. And the square root of 1 is 1. So we can normalize a vector by dividing by its magnitude. Again, that's hopefully something you've done in previous mathematics courses. I don't want to spend too much time on that right now. I just want to look at what happens if we have a set of normalized vectors. An orthonormal set is an orthogonal set of normalized vectors. Whenever we have an orthogonal set, we can easily divide by magnitude in all the vectors. That will give us an orthonormal set. And to compress language even further, an orthonormal basis is an orthonormal set which is a basis for a vector space. All right. So my theorem here is going to look incredibly similar to the theorem we just looked at. Let's let W be a subset of Rn. And I'm going to insist that it is a subspace. Let's let S be a set of vectors. I'm going to use Q's, right? Q1, Q2, all the way through to Qk. And this time we have an orthonormal basis for W. And let's let little w be an element of set big W. That doesn't really look like a W. That looks a little bit more like a W. Then we have this very simple way of writing this out. Vector W has an unique way of being written as a linear combination of the vectors q1, q2 up through to qk. And the coefficients can all be found by taking dot products, w dot q1, w dot q2, down through to w dot qk. I'm not going to take the time to write out the proof for this because I built it up for you. Take the theorem that we just proved, use that result here, and then use the fact that the norm of Q is 1 because it's an orthonormal basis, which means all the vectors have been normalized. Instead, I want to look at one last exercise. I would like you to prove that the set square root of 2 over 2, square root of 2 over 2, square root of 2 over 2, negative square root of 2 over 2, forms an orthonormal basis for R2. All right. So to give you kind of a guideline of where to go, you need to show that this is an orthogonal set. You need to show that all of the vectors in the set have been normalized. And the toughest one, which is also the easiest one, you need to show that this is a basis for R2. I will let you know that there is a really nice, easy theorem we can use on this if you look back at what we talked about when we said bases, and we first defined the basis for a vector set, the basis for a vector space, and the dimension of a vector space. So that's the one thing that you may want to look back on if you don't remember it offhand. The other two parts are things that we just did in this video, so hopefully not that bad. Take a couple of minutes, see what you can do with that, and I'll see you in the next video.